Hello and welcome to everyone. How nice to see all of you here tonight. Today is the fifth and the last day of Maths Week, which is held by Koç University Science Club and Bristol University Math Club. Today there will be a speech by Professor Dr. Varga Kalantarov, which is the last talk of the event. Welcome, and we hope that this event will be productive and pleasant for all of us. We want to say thank you to Professor Dr. Varga Kalantarov from Koç University's Mathematics Department as all participants for accepting us. Now, I will leave you along with Varga Kalantarov and his speech on stability and instability of solutions to non-linear differential equations. And also, please mute your phones. Now you can use the chat box to ask any questions, and I'm leaving you with Doctor. Thank you.
Okay, but let me share screen. Seems that you okay. No, now let me. But it didn't open there. I don't understand why. You know, I shared my screen here.
Yes, you shared your screen here. It's fine.
But
we all can see.
But you can. Do you see my title and everything? But I don't see here.
PDF'i mi açmak istiyorsunuz?
Yes, açtım zaten. Burada.
Hocam direkt PDF'i açıp onun üzerinde düzenlemeye basabilirsiniz belki. Şu an notların üzerine onu yapıştırmışsınız. O yüzden olmuyor galiba. Çok da iyi anlamıyorum ama.
You know, usually I do the same in the class when teaching.
Tekrar deneyin isterseniz. Çünkü sadece PDF dosyasını şu an yapmış gözüküyorsunuz.
Okay, now let me try to
Notların üzerine.
Let me open this one here. That's okay. Moment, please. So thank you for advice. Now perhaps I will succeed. This one, very good, very good. Okay. So I hope you see, of course, here you see me in the. Do you see?
Evet hocam, şu an gayet gözüküyoruz.
We can see. Everything is fine.
Everything. You see me here in the class?
Yes, we do.
Very good, very good. So, you know, my title is the stability and instability. Please.
İsterseniz kamerayı değiştirebilirsiniz. Biraz uzak, gözükmeyebilir yazınca.
Okay.
İkinci dense bire falan alıp onu yapabilirsiniz. Onun dışında görüyoruz.
Yes. I'll do that one now.
Okay.
Just a moment.
We will switch the camera and then we will go on.
Okay.
So, it's all to yours now. I'm just muting myself.
See.
Thank you for your help, Saray.
Okay.
Welcome every time.
That's good now?
Yes.
Perfect.
Okay. So, actually, I will speak about differential equations, about the properties of solutions of differential equations, about why we study differential equations. And then I will, of course, touch the questions which we are not speaking about during the lectures in the course Math 204 course, in the course of standard course of differential equations for undergraduate students. Let me start with showing some pictures. You know, Newton was one of the first mathematicians who used differential equations in his studies, in his discoveries. And Leibniz, of course, was one of the first who solved one of the first differential equations. I would like to show you the following. Do you see now everything here? You see my screen?
Yes, we do. Yes. We do.
Okay. So the main Newton, in his famous principles of mathematical principles of natural philosophy, he wrote an anagram, and the meaning of that anagram was that main thing is to may solve differential equations, that all the actually models of nature are written in the form of differential equations. And the second mathematician who started studying differential equations, started solving differential equations and using differential equations in his studies was Leibniz. The problem is that before Newton and Leibniz, mathematics was static. By using mathematics, scientists, people, they were solving some problems, static problems, calculating some volumes, calculating areas, also not of every figure or every plane or space figure. But discovery of differential equations, differential and integral calculus allowed us to understand some dynamical problems, allows to people to describe mathematically dynamics, to describe those processes we are changing when time goes on. And one of the first very important, one of the first mathematicians used the differential equations in his studies was Leonhard Euler. So what we study in differential equations? In differential equations, we are studying equations, of course, but what is a differential equation? A differential equation is, you know, that it is an equation which involves a function. And an equation is called a differential equation if it involves some function, but not only the function, but some derivative or derivatives of a function. So a differential equation is an equation of the form I'm writing general form of differential equation, ordinary differential equation. You can write y prime, and y to n is equal to 0. Here, t is the independent variable y, and its derivatives are y is the unknown function, and an equation involves some derivatives of a function. What we do in the study of differential equations, in undergraduate study of differential equations, usually we solve some concrete differential equations. We explain you how to solve, for instance, second order differential equations with constant coefficients. We explain you how to solve some first order equations, separable equations, or exact equations. We are using integrating factors to find the solutions of some equations which are not exact. We discuss also the problem of existence of solution of the initial value problem for this kind of equation. When you are given some differential equation under some initial condition. And we prove a theorem which asserts that if the function f and its partial derivative with respect to second variable are continuous functions on some rectangle, then this problem has a solution on some small interval. And moreover, it has a solution, but that solution is also a unique solution. The problem is, what we have to do after this? You know that equation has a solution. You can solve some simple linear equations, some simple nonlinear equations, some higher order equations, but not each higher order equation. We know how to solve each higher order equation with constant coefficients. We can present some solution of the equation, but most of the problems of physics, chemistry, of other sciences are leading not to linear equations. They are leading to some nonlinear equations. And here, not only nonlinear, but the equations which we usually cannot solve in the sense we are discussed during the lectures in the course of undergraduate course of differential equations. But what to do if you cannot find explicit solution of the equation? You have to know something about the solution. You have to discuss this problem. You have to try to find some properties of solution, even if you cannot find explicit form of the solution. Even for the first order equation, you cannot find in each case the explicit form of solution. You have to then analyze the solutions of the equation. Therefore, it is important to know whether the solution is unique, whether the solution is bounded or not, whether the solution tends to infinity as t goes to infinity, or it is decaying to zero as t goes to infinity. Or the following question: what if you have two solutions? Imagine that y is a solution of this equation and z is a solution of the same equation with different initial value. The question is, what you can tell about the difference of these two solutions if you know that difference between initial values is small enough on some interval? Can you claim that, or can you assert that the corresponding solutions are also close to each other? This question is the question of stability of solution or continuous dependence of solutions on initial data. Or imagine that you have an equation, very simple equation, y prime t, plus I am writing very simple equation. We discussed this equation during the lectures. You have an equation of this form where ht is some function. Unique thing you know about this function is that this function is tending to zero as t goes to infinity. What you can tell about the solution of this equation which satisfies some initial condition? Of course, the answer to this question depends on the value of the parameter a you have here. So you can show that if a is positive, then all solutions of this equation are tending to zero as t goes to infinity. Though you cannot find the explicit solution of this equation. Of course, you can find the solution in the sense in the form of integral, but you don't know what kind of function ht you have there. Maybe you will not be able to calculate the integral of ht. But if you know that ht is tending to zero, you can, by using the L'Hopital's rule, show that all solutions are tending to zero. So I will continue to speak about differential equations and I will show you some interesting examples. But please don't hesitate to stop me and ask questions if something is not understandable, or if you have some question, either even not related to topic of my talk, but in some way related to differential equations. So as you remember, we were calling the initial value problem for the ordinary differential equation of that form the Cauchy problem. Cauchy was one of the first mathematicians studied the problem of existence of solutions of the first order equations under some initial conditions. So there are many problems leading to systems of differential equations. Have you seen this system? Who have seen this system I'm showing you here? Who are here in the audience? I don't know how many people we have here. And who have seen this system? Please tell me. Nobody would like to talk.
Someone sees them named. They're texting to chat.
Please let them ask questions directly. No need to mute them. Let them ask questions. If somebody would like to ask questions, let him open his microphone and ask questions.
Okay.
Please.
Okay.
This will be much interesting and more useful, I think. Please, you can ask your question. Okay. So, imagine that you have this kind of system written here. I wrote here the so-called Lotka-Volterra system, which has interesting applications in genetic of populations, in many other fields of physics, chemistry, biology, and try to solve this system of equations. You see, the system is not linear. It is a system of first order ordinary differential equations, but nonlinear. If you try to find the explicit solution of this solution of the initial value problem for this system of equations, you will have some difficulties. But we are able to understand the behavior of solutions of this equation. I would like to show you also another system, the system which is called the Lorentz system. the Lorentz system is a system of ordinary differential equations, which is kind of simplification of the Navier-Stokes equations, the equations which are describing the motion of the fluid in some channel, or the dynamics of fluid. And first, it was in the end of 60s, the Australian meteorologist Lorentz discovered very interesting property of solutions of this system. You cannot predict the solution of this system at the infinity. The behavior of solution of this system of equations when t goes to infinity is very strange, and this behavior is called the set I am showing you is called the strange attractor. It is the set which attracts all solutions of this system as t goes to infinity. And the interesting property of this set is that the trajectory on this attractor is moving on some plane. You see this the round motion, and then suddenly it is dropping to another plane and moving there, and then again randomly is going back and moving there. So the theory of differential equations, the qualitative theory of differential equations, is very interesting and rich theory. And unfortunately, during the undergraduate course of differential equations, we are not able to speak about this kind of problems, to discuss this kind of problems. But I would like to speak today about let me show one more picture, and then I will speak about the problems I am going to discuss a bit later. This system of equations also is very interesting system of equations. It's called Belousov-Zhabotinsky system. It is also, I think, end of 50s, the Russian chemist, I'm sorry, Belousov, he made some chemical, he studied some chemical reaction. He mixed some acid and some oil. I don't remember the names of these substances, and he discovered very interesting behavior of this mixture. This mixture behaved like some oscillating process. You have some picture of this sort, and then after some time that picture changed and appears the same picture, and he discovered actually the oscillating chemical reaction. And after sending the paper to the journal, of course the journal rejected, because that time it was the chemist is told that it is nonsense, that the problem that the result obtained is absolutely wrong. And just after 15 or 20 years after publication of that paper, the other chemist and actually mathematician Zhabotinsky repeated that reaction and justified the discovery of Belousov. And using the system of ordinary differential equations, he could model this chemical process. But you know that not everything in our life is good. Not everything is smooth. But in some situations, you have some problems where the solutions become not even continuous. Allow me to show you a very simple example. You actually have seen this example during the lecture. And today I am going to speak first about this kind of problems. And then, if time allows, I will speak about stability of solutions of differential equations. I'm repeating again, if you have any questions, don't hesitate to ask, please. So imagine that you have an equation of this form, first order ordinary differential equation under the initial condition, y at the point 0 is 1. It is very simple equation. Actually, it is simplification of some model of kinetics of chemical reactions. Imagine that Yt is a temperature appears when during some chemical reaction. And the rate of change of temperature is proportional to square of that amount of temperature. And at the initial moment, you have temperature is equal to 1, initial moment. And the reaction is continuing. So you can easily find solution of this equation. The solution of this equation is this function. Yt is 1 over 1 minus t. I told to my students what to do after finding this solution. Who can tell me what you would recommend to chemists who found this solution of this equation under this initial condition? Please. Please unmute, ask your microphone and ask question. I cannot read your question.
To run away?
Of course, as quick as you can. Because when t goes to infinity, to 1 from the left, this function will tend to infinity. So you see that solving this simple ordinary differential equation, knowing how to solve this simple differential equation under some initial condition, you can survive. You can survive in your laboratory from some kind of tragedy. You know, not all equations are ordinary differential equations. Many problems of mathematical physics, of other fields of science are described by partial differential equations. Soon in the course of Math 204, we will study together with you this so-called heat equation you see here, and the wave equation. This and this. You even can, we will find the solution of this equation under some initial and boundary conditions. Write the explicit solution, write the solution of this equation. But if your equation is not linear, then in general you cannot do that. If you have this equation, we are not able to find explicit solution of this equation. You see, very simple equation. Here u is a function of two variables, x and t. And you see to the left the heat operator, and to the right hand side u squared. The question is, has this problem a solution or not? Or if it has a solution, what you can tell about this solution? Actually, I wrote a very simple case of the nonlinear partial differential equation under these boundary conditions. You can easily see that actually there is a theorem which asserts that if your initial functions are sufficiently smooth, then this problem has a solution on some small interval, time interval. But even if you don't know how to solve this problem, you can show that some solutions of this equation behave like this one. They tend to infinity in a finite time. Why? You can easily check that. This function ut is equal to y0 divided by 1 minus u0t. Assume that u0 is some positive number, fixed number. Is the solution of this partial differential equation, because derivative of this function with respect to x will be 0 because it is not depending on x. And then you see that even for partial differential equations, you may have solutions that tend to infinity in a finite time. So this kind of processes, they really appear in the study of many phenomena. And now I will prove a very simple but very beautiful theorem which you can use in the study of ordinary differential equations, in the study of partial differential equations. But the theorem I am going to prove is simple, and every student of who knows Calculus 106 can understand how to prove this statement. So theorem or lemma is the following one. Suppose that you have a function of one variable, psi t, twice continuously differentiable for positive values of t. And you know that second derivative of this function multiplied by the function itself minus 1 plus alpha psi prime squared is not greater than 0 for t greater than 0. The unique thing you know is this. And assume that the psi at the point 0 is positive. Psi prime at the point 0 is I'll tell is also positive. Now I will see, maybe it is, I have to write here negative, but patience, a bit later we will know. Then if these conditions are satisfied, then there exists some t0 sometime such that limit of this function when t goes to t0 from the left is infinity. Of course, you can ask me, not differential equation, but inequality. How we are going to use this inequality to study differential equations. A bit later, I will show you. But how to prove this? To prove this, I would like to show you some pictures. Let us sketch some picture. Imagine that you have a function, say phi t. You know that phi at the point 0 is positive. So it is phi 0, it is 0. It is t-axis. You know that this function at the initial moment is positive, and its derivative, phi prime at the point 0, is negative. You know more. You know that derivative, second derivative of this function is non-positive for each t. What you can tell about this function? Let's try to understand. What we know that at the initial moment, the value of the function is positive. And derivative of this function at the initial moment is negative. It means that the tangent line to graph of this function has this kind of slope, okay? And you know that second derivative of the function is negative. What we know about the functions which have second derivative negative, non-positive. We know that this kind of functions are concave. And concave functions, you know that they always lie below of each their tangent line. So then our function phi t, of course, it must have this kind of graph. So its graph must be lying below of its tangent line. What follows from this one? From this one, it follows that there exists some point t0. There exists some point t0 such that phi t tends to 0 as t goes to t0 from the left. Now, let me consider the function psi t. Just I wrote, let me consider the following function. Not that one, but some function of this sort. Let me write, consider phi t is equal psi t to the power minus alpha, where alpha is some positive number. Allow me to calculate derivative of phi with respect to t. What I will have here? Then it will equal minus alpha, psi to minus alpha minus 1 t times psi prime t, right? Second derivative of phi will be alpha plus 1, derivative of this one, minus one more minus from here. I am getting this. And psi to minus alpha minus 2, one more psi squared, psi prime t squared. And then minus alpha psi to minus alpha minus 1 t multiplied by second derivative of psi. See? I hope everything is clear here for you. Then,
yes.
Let me continue here. Not here. Let me continue somewhere here. You have this equality I can rewrite in the following form. Alpha minus alpha, better to say minus alpha, multiplied by the following one. Minus alpha even this, minus alpha psi 2 minus alpha minus 2t, we can easily calculate what I am, that this expression is equal to what I am going to write here. Psi double prime t multiplied by psi t minus alpha plus 1 psi prime t squared. Okay? Now pay attention. Here in the square brackets, we have that expression I wrote there above. So if this one is positive, then the whole expression is non-positive. If this one is non-negative, then the whole expression is non-negative. From this one, it follows that then your function phi of t is a concave function. Is a concave function. But now phi at the point 0 is psi. Remember that alpha is some positive number. Psi at the point 0. I assume that it is positive, and then phi prime at the point 0 is minus alpha, psi 2 minus alpha minus 1 at the point 0 multiplied by psi prime at the point 0. So I see that if psi prime at the point 0 is positive, then derivative of the function phi at the point 0 is negative. So I see that really my function phi behaves like this one. And when solving some problems for differential equations, you can use this trick. Even if you don't know how to solve the equation, how to find the explicit solution, you can use this theorem to find those values of those initial values for which the solution may belong in a finite time. But it means that you are revealing the character of motion or of the dynamic of the process you are studying. Actually, I would like to show you some simple examples. And then maybe we will speak about other kind of problems. Maybe it's reasonable to speak about ordinary differential equations, not partial differential equations. Would you like me to speak about partial differential equations or ordinary differential equations? Please tell me.
Partial differentials.
It will be good. Okay. So I will now show one example of very important and interesting partial differential equations, which is very simple actually. Imagine that you have an equation of this form. This equation is called a Burger's equation. It describes the waves. It is one of the important nonlinear wave equations. Imagine that you have an equation. X is moving on whole real axis. So u is a function of two variables. And you have this kind of equation. But it's very simple, right? Calculate the solution of this equation. Actually, there is a method in the course of differential equations. You will learn that there is a method of finding solution of this kind of equation. And by using that method, you can also see, you can also understand that some solutions of this equation also are unstable. They're not only unstable, they are breaking down after a finite time. Like, you see some waves on the sea, they are very smooth, but approaching the shore, they are breaking down. So I will show that one, how to show this process by using the theorem just I formulated here. Imagine that you have this kind of initial condition. So you have an equation and the initial condition. Let me write here fx. I assume that the initial condition, initial function, is a very smooth function, which is decaying at the infinity. When x goes to infinity, plus or minus, the function itself, and all of its derivatives are tending to zero rapidly enough. Then let me consider the following function, psi t, which is equal integral our whole real axis of u derivative of u with respect to x. So the integral of square of derivative with respect to space variable. And here, let us calculate the derivative of psi with respect to t. You are taking derivative with respect to t of this integral, since you consider x as if as a constant, then you will get the following one. It is 2 times integral. Allow me not to write here r. You know that it's integral over whole real axis. It will ux xt multiplied by uxx xt uxt. Sorry, uxt xt dx. So you took derivative of this one with respect to t. And now integrating by parts, I know that my function is decaying at the infinity. So sorry, here I have to charge my computer. I brought not that. So soon the. I'm very sorry. Soon the. Here. Okay. Unfortunately, let me show some pictures. Unfortunately, soon my second computer will stop.
No worries, it's okay.
I cannot charge. Let me show some pictures of. I will bring now this charger from my room. I'm sorry. Please wait 3 minutes. I will be back in 3 minutes.
Okay.
Okay. So, I'm very sorry for this inconvenience. Where is my charger? Here. Okay. Do you still hear? Okay, now let me continue then. Do you hear me?
Yes, we
can
do.
hear.
Okay, thank you, thank you. So then I have this one, -2. I'm integrating by parts, you know. This one is my V, this one is, not, let me write this way. G, it is Fx. Fx. Then I can write this in the following for -2 times integral of Uxx. Allow me not to write arguments. T dx. Of course, you can tell me what where what about the values of the function on the boundary? But we don't have a boundary, but our function is defined on whole real axis, and since it is tending to 0 at infinity, the boundary integrals disappear. Now let me use the equation. It is equal -2 integral Uxx times Ux dx. Okay, but this one I can write in the following form: minus integral Ux squared divided by our x multiplied by U dx. Agree with me? Take derivative of this one, you will get this. This multiplied by this, and one U here. Integrate once more by integrating by parts. Once more, you are getting here integral of Ux to the power 3 dx. So let me write it here. I got the following one. Derivative of my functions at the point t is equal integral of Ux to the power 3 dx. Remember this. And now allow me to calculate second derivative of psi. So you see, we are all the operations we are making here are very simple operations. Integrating by parts of function actually of one variable with respect to x. We can think about this one as a function of x only. Then second derivative of psi will be derivative of the first derivative of psi. But first derivative is this integral of Ux to the power 3 dx. Again, taking derivative, you will get 3 times integral Ux squared dx. Sorry, 3 times Ux squared dx times Uxx dx. Uxt. Taking derivative with respect to t. This one is integrating by parts because with respect to x, will give me 2 here, 3 here, -6 integral Uxx multiplied by ut dx. Please check my calculations. I can cheat you. Okay, this one is equal. Now what we see here, we got here one more ut. Then I can write this in the following form. It is -6 integral Uxx multiplied, instead of ut, I am writing what is ut. Remember, ut is u multiplied by ux. It gives me ux, and here then I write square dx. Okay?
Okay.
But sorry, question?
Not question. I just answered you.
Okay, very good, very good. Everything's okay, I hope. Okay, instead of ut, I wrote ux, and then got this. But this one, again, I can write in the following form. This one I can write as 1/3 of ux to the power 3 derivative with respect to x. Then I get minus 2 times integral ux to the power 3 x multiplied by u dx. And finally, one more integration. Moment, please. Ux squared. Yes, and finally you'll get this. It is equal to 2 times integral ux to the power 4 dx. Okay?
Okay.
Okay. Now let us calculate, let us consider what is psi double prime. Psi double prime t multiplied by psi t is, I'm writing this 2 times integral psi t was ux squared dx multiplied this one, you see, integral ux to the power 4 dx. What was psi prime t squared? Let's see, psi prime t squared. You know that psi prime t is, we have seen, integral ux to the power 3 dx squared. And now I finish all my calculations with the following last line, psi prime t multiplied by psi t. I know that psi prime t minus, let me write 2 times psi prime t squared is equal to the following expression. Psi 2 times integral ux squared dx multiplied by integral of ux to the power t dx minus 2 times integral of ux to the power 3 dx. I claim that this expression is non-negative. Who can tell me why? Please. It is very simple question. You have to know this. In the course of calculus, you have learned the following inequality, which is called the Cauchy inequality. F of g, f multiplied by g dx, absolute value, it is not greater than, take it square, it is f squared dx integral g squared dx.
Can I ask something?
Please, please.
In the right part of the, yes, in this equation.
Yes, square. Yes, square, sorry, square. Okay, you mean this?
Yes, yes.
So I forgot to write square. Thank you very much for this.
But I have one more question. If this is the square and we have the -2, how can we say that it's positive?
So I am explaining that one. So this one is positive, right?
Yes.
Positive, positive. We are subtracting this expression. Anyway, I'm saying it is the whole, this difference is non-negative. Why I am explaining? We are using the Cauchy's inequality. Look, integral of ux to the power 3 dx, according to the Cauchy's inequality, is not, you can write this integral in the following form. It is integral ux multiplied by ux squared dx, right? You see? Then here you use the Cauchy inequality or Hölder inequality with p is equal to 2. It is not greater than integral ux squared dx, square root of the first, 1/2, multiplied by the integral of ux square of this one will give you 4 dx, 1/2. Okay, and then you can do the following one. Take your eraser, erase this one, write here squared, and then and erase this 1/2 here and 1/2 here. Therefore, you see that this difference is non-negative. Okay, and now you can easily use the lemma, the statement just I showed you. from this one, it follows that I don't want to calculate the values of the initial function for which this one is true. It follows that integral of ux squared dx tends to infinity as t goes to some t0 for a large class of rich class of initial functions. Do you have any questions here? No questions. Okay.
I have a question.
Please.
What kind of observations lead to this lemma? So we get that this lemma holds, but how do you get the lemma, the idea in the first place?
The lemma is some auxiliary tool to study differential equations. You know, the idea was to understand how to. I use this lemma for this very simple example. Actually, you can use this lemma to study, for instance, this kind of problem. Try to do that from yourself at home, by the way. Imagine that you have a system of equations which you can write in this form. I'll show you now. So the lemma appeared when studying some nonlinear wave equations, much more complicated than I showed you. I showed this example just to demonstrate how this lemma works. But you can use this lemma to study the following type of ordinary differential equation or system of differential equations. Imagine that you have the following type of system of differential equations. Plus a u is equal, let me write here this one, u squared times u. Here you can imagine that u is a vector, if you wish, that n-dimensional vector function depending on t. This one means u1 squared plus un squared. A is some symmetric positive definite matrix. Which positive definite means that for each side from Rn, it is not lesser than some a0 positive multiplied by xi squared. So you can use this lemma to show that the initial value problem for this system of equations. If you wish, I can write here derivative in this form. Then the solution of the initial value problem tends to infinity as t goes to some finite t0. So for some initial vectors, solutions of this equation are tending to infinity in a finite time. It means that the Cauchy problem for this equation actually is an unstable problem. You cannot even prove that your solutions are bounded. So the model we consider describes your process just on a finite time interval. And how to show that one? Just let me write the function which you can use to discuss this problem. This, and try and use this limit. You can show that psi double prime, psi minus psi 1 squared t for some alpha I don't remember, some positive number is non-negative, and use the lemma. Not only for this equation, you can use it for some other type of partial differential equations, ordinary differential equations, and get interesting results. Are you satisfied with my answer, or who was asking?
Thank you for your answer.
Okay. So, how much time I have?
How much time you need?
I understood you wish me to finish as soon as it's possible. Okay.
No, we are really pleased that listening to you.
Okay. So you know, I don't want to bother you with bore you with calculations. Maybe I like books with pictures, and let me show some pictures. Hope you also like to see some pictures. So there are some other ways of proving this kind of theorems. I don't remember whether I wrote it here or not. let me just show Jensen inequality. Maybe this one is very interesting, just to see. I will not prove, I can also prove the theorem using this Jensen inequality, we can obtain similar results. We can use this inequality to show that some solutions of some heat equations, some wave equations, nonlinear one, they blow up in a finite time. What is saying this inequality? It's very interesting inequality. By the way, I hope you, some of you know the Jensen inequality for convex functions. The Jensen inequality, standard Jensen inequality is this one. If your function satisfies this property, alpha x plus 1 minus alpha y is not greater than alpha fx plus 1 minus alpha fy, then this function is a convex function. But there is an analog of the Jensen inequality for integrals. It is very beautiful inequality which has very interesting applications. Imagine that you have a function f, which is convex function. Psi is a positive function. For simplicity, even you may assume that the integral of psi is equal to 1, but I wrote here the general type. Then this kind of inequality holds true. It is very interesting inequality, and I recommend you to find the proof of this inequality in the book of Hardy, Littlewood, Polya. There is a very interesting book. Maybe you can find its last edition in internet. Hardy, Littlewood, Polya, Inequalities. The book was written by a famous English mathematician, Hardy, Littlewood, and Polya. And we can use this inequality to, actually I wrote here the proof, but since I don't have enough time, I am not giving that one. We can use it to show the blow up of solutions of some heat equations. Let me go ahead and then let me show you some, maybe it's all about, I can send this slides to you if you wish. I would like to show you the pictures of Navier and Stokes. You know that the Navier and Stokes, they independently derived the famous Navier-Stokes equations. Now we are calling them Navier-Stokes equations, the equations which are describing the motion of liquid in channels. And they have this form. It is complicated. It is actually not complicated equation, but it is very difficult to study the behavior of solutions of this equation in three-dimensional case. And there is a millennium problem which you know, maybe some of you can solve if you show that the initial boundary value problem for this equation has a smooth solution with smooth initial functions. Then you will get $1 million and be very famous in whole world. Some equation, very simple equation, which is describing the motion of the water in a shallow water in a channel, the so-called Korteweg-de Vries equation. And now I show you this equation, this called the nonlinear Schrödinger equation. And why I show this picture, because this equation is describing the process of tsunami. You know the equation I showed you also has a solution whose derivative is blowing up in a finite time. Derivative blowing in a finite time means that the amplitude of solution is finite, but it is breakdown. The derivative is breaking down in a finite time. And some pictures, you know, here you see I would like to show you three famous mathematicians who contributed in differential equations and analysis. First one is Jean Leray, who first discussed the mathematical analysis of Navier-Stokes equations in the sense of existence and uniqueness. Sergei Sobolev and Laurent Schwartz, who invented the mathematical theory of distributions. You study engineers in the course of in which course, in the signals and system, you study distributions and calling a distribution a function which is everywhere continuous, infinitely differentiable, but equal to infinity at a given point. Each mathematician will, of course, laugh at this kind of definition, but sometimes you use this kind of definitions and succeed in solving the problems. And finally, I would like to show you three also very famous mathematicians working in the field of, they worked in the field of mathematics. All of them passed away. but they contributed a lot in the problems I discussed together with you today. And I think I stop here. I'll be very glad if you have some questions. You ask, you didn't ask questions during the lecture. You know, maybe now you can ask. So, did you understand something I told about? You know, you can send
it was
message. We can discuss. You know, my aim was to show that there is some different word of differential equation, not just that word you see in the course of Math 204.
Even if my major is not maths, I really understand some basic things in this lesson.
I am very happy.
So I'm so glad and I'm so thankful to you.
Thank you very much.
It was a wonderful session, and I really like to thank to you for enlightening us and accepting us.
Thank you very much. Thank you very much. I am very happy to hear this kind of words from you. Thank you very much. Thank you very much. Anyway, maybe if you have, thank you very much. Maybe someone has a question. Maybe you would like me to send something the question might be not related to topic I discussed here, but of course on mathematics, you can ask some questions on differential equations, related topics.
There is one student who is asking on message.
Please.
Let him ask. There is a student who is asking about hypergeometric differential equations.
I see. You know, hypergeometric differential equations are very interesting equations. You know, there is some theory of hypergeometric equations. It is some special topic. The topic I was trying to speak about today is a different one. You know, in that theory, you would like to find solutions of these equations, but here our aim is not to give explicit solutions of solution of a given equation. Our aim is to discuss the model, to understand the behavior of solutions. So, you know, I didn't show the solution of the Burger's equation we discussed here. Even you cannot find the solution of this system of equations, explicit solution, believe me, in general case. But we have some tools to understand the behavior of solutions. It's interesting. There are some problems of this sort. Given an equation, for instance, in the theory of sinuous and systems, imagine that you have an equation of this form. This telegraph equation, ut t xt plus gamma ut xt minus uxx xt, and to the right hand side is given a function uxt. You have boundary conditions. The question is, the function h is a periodic function with respect to t. Can you show that the solution of this equation is periodic? Or you may have here nonlinear equation. Has a given nonlinear equation a periodic solution, periodic with respect to time solution? These are questions we are trying to answer in general. We are studying those equations which we cannot find the explicit solutions of them, but we can estimate solutions. We can say something about solutions. We can say that you know I cannot calculate the solutions, but I am sure that the solution will tend to 0 as t goes to infinity. Or I am sure that if the initial functions are satisfying these conditions, then my solution will tend to infinity in a finite time, even though I cannot calculate that solution. So the topics I would like you to think about is this kind of topic. These topics are called in the theory of differential equations, qualitative theory of differential equations. You are not solving problems, you are not finding explicit solutions as we do in the course of Math 204, but we can analyze the problem and say something about solutions, which is interesting, of course, from the point of view of applications and from a theoretical point of view. But hypergeometric equations are very interesting equations, and you can find enough material in literature. Write down in the internet hypergeometric equations, and you will find a series of books devoted.
Apologies
can I ask a
for
question?
interrupting.
Yes, please.
In this seminar, you've shown us quite a few equations, but is there any nice work that compiles the heuristics that gives the equations themselves through physical or mathematical considerations? For example, Navier-Stokes equations, I can search on it online and find some heuristic derivation of the equation itself, but is there any book you know that compiles equations and their heuristic derivations from physical considerations?
There are lots of books of that sort. If you would like to start, you would like to find derivation of Navier-Stokes equations, there is a very old book of Lamb. The book is called Hydrodynamics. There is a book of Batchelor, which is also called Hydrodynamics. There are books named Navier-Stokes equations. For instance, for derivation of Navier-Stokes equations, I can recommend you the book of Temam and Miranville. There are many other books. Kibel, Koch, and drop me a mail. I will send you the list of books which you can use to understand how to derive Navier-Stokes equations. And even there are books devoted to the qualitative theory of Navier-Stokes equations. About 10 books appeared last I think 40 years. Just drop me a mail. I will send you the usual literature, the necessary literature.
Okay, thank you, Hocam.
You're welcome. Please, other questions?
Hocam, I have a question. It's not related to topic, but I really wanted to ask you. Have you read A Mathematician's Apology?
Yes, I read that book. By the way, I read that book in Turkish. I didn't have it in English. I read the Turkish translation of this book made by late Tosun Terzioğlu.
I read that too, and I really like that.
Very nice book.
I would like to recommend you. Yes.
Yeah. By the way, I recommend you to read another book of the co-author of Hardy. You know that Hardy wrote many of his papers together with Littlewood. And there is a book of Littlewood. I strongly recommend to read it, especially engineers. The book is called Mathematical Miscellanea. Very interesting book. You will find very amazing information there. Very interesting. Very interesting information about mathematics, about the life of mathematicians, about Ramanujan, about Hardy. And it's very interesting. It's very interesting book. By the way, let me maybe remember some small, not anecdote, but real fact. You know, they wrote a paper together with Hardy. Hardy wrote a paper. I read the paper and asked Littlewood to check whether there are some misprints or some errors. Littlewood read everything, and then next day he gave back the paper and said that Hardy asked, could you find something not correct? Is there something not good? And Littlewood said, yes, there is very important error there. And Hardy, astonished, why? We checked, we discussed together with the whole paper. And Littlewood answer was that the name of Hardy was written not correct in the title of the book. The name of the Hardy was written not good. So this kind of stories you can find in that interesting book. Other questions, maybe about equations, about calculus. You know, I am saying to my students that, you know, don't say the topic, the course Math 106 and Math 203 calculus. Calculus is kind of you know, it is nickname of the real name of the topic. It is differential and integral calculus. We are studying differentials and integrals. So try to repeat those topics you studied in course of 106 and 203 to understand differential equations, and in the future it will be very useful for you engineers, mathematicians, physicists, and others. Other questions? So you're tired, I see. If you have questions, don't hesitate to ask. I can send you any literature about any topic I spoke about. I mean, at least the site references.
I think
what
we don't
department
have
are you?
any questions.
What's your
Pardon?
department, Doğa?
It's molecular biology and genetics.
Very good. Actually, you know, then allow me to show you last slide. I was planning to speak about, but I didn't do that. Have you heard the names Hodgkin and Huxley? Hodgkin and Huxley, they were famous English scientists in the field of.
Yes, Mr. Huxley, I heard him.
Yes, and many mathematical works are devoted to this Hodgkin-Huxley system of equations, the qualitative behavior of solutions of Hodgkin-Huxley system. There is a simplification of the Hodgkin-Huxley system, which is called Fitzhugh-Nagumo system. It is a system of two equations. One is the ordinary differential equation, another one nonlinear parabolic equation, which is describing the transmission of impulses in neurons and axons. It is very interesting system, and in order to understand what happens there, you have to study this equation from the point of view we discussed together with you, to study the behavior of solutions. You cannot actually find the explicit solution of the problems that appear there, but you can say a lot by analyzing the models. You know that the Hodgkin and Huxley got Nobel Prize for that?
Yes, yes, I do. About DNA.
Okay. Okay, guys, if you have questions, I'm ready to answer. If not, then I'm very glad that you attended the seminar, and it was nice to be together with you, though I don't see you.
We are also. Okay, Doğa, go on, please.
You can go on.
Hocam, also we are very grateful to see you in our event, and your contribution is so valuable for us. We want to see you in upcoming events also because of that. Thank you for your speech and your contribution, your preliminary work, your everything. That was a great talks, I guess, and everybody like it, as I can see in the chat box.
Thank you very much. Thank you very much.